Okay, so hello and welcome back. So in the previous videos we talked about some definitions, and we also talked about three different situations in which the lines were coincident, parallel, and also intersecting. Now what we want to do now is basically talk about a couple of different types of definitions and related to these lines, and these are basically useful in the case where the lines intersect, or the lines are parallel, or the lines are coincident. So basically there are basically three ideas here that need our attention. One of them is called an inconsistent pair of linear equations. The other one is called a consistent pair of linear equations, and the other one is called a dependent pair of linear equations. And each of them is basically a simple definition. So if a pair of linear equations has no solutions, that's called an inconsistent pair of linear equations. So here your pair has no solutions. No solutions meaning that, for example, either meaning that the lines are basically never intersect. For example, you have if the two lines are intersecting, of course, then you have a solution over here, and that would be a consistent pair of linear equations. If the two lines are coincident, meaning that both of the lines are represented by this line, again you have infinitely many solutions. It's not that you don't have any solutions. But if the two lines are basically parallel, like this, then of course, as you can see, the lines are not intersecting at any point, and that's basically the case of an inconsistent pair of linear equations. A consistent pair of linear equations is basically a pair of linear equations in two variables, of course, which has a solution. So here, which has a solution. Basically a pair of linear equations which has a solution is called a consistent pair of linear equations. And basically in the case that basically we had this case over here where basically the two lines were coincident. So let's say that you have a pair of basically you have a pair of linear equations, and both of the lines are represented by this line over here, meaning that the two lines are actually coincident. So what that means, that a pair of linear equations which are equivalent, so this pair of linear equations has infinitely many distinct common solutions. Infinitely many distinct common solutions. Again, imagine that these are basically two lines, and you have drawn the two lines, and you've gotten the exact same line for both of the equations. So they have infinitely many distinct common solutions, and such a pair is called a dependent pair of linear equations in two variables. So that's called a dependent pair of linear equations in two variables. And of course, you know that a dependent pair, since you have infinitely many distinct common solutions, is always consistent. Okay, so that is that. Now, now in order to summarize this whole thing, what we can say is that basically we had three different cases. We had three different cases where the two lines intersect at a point. So we had intersecting lines, and we had basically parallel lines, and we had coincident lines. Okay, so when the two lines are intersecting, of course you know that you have a solution, and so you have a consistent pair of linear equations. So that's basically consistent, right? And when the two lines are parallel, of course you know you have no solution. So this is an inconsistent pair of linear equations. Okay, and then when the two lines are coincident, and in which case you have infinitely many solutions, that's basically that's also consistent because you have many solutions there. That's a consistent pair of linear equations, but it's also dependent. So it's also dependent. Okay, so it's basically called, you can even use the word dependent alone, and because dependent automatically implies consistency, meaning that if you say a dependent pair of linear equations, if you say dependent pair of linear equations, that means a pair of lines that are actually coincident or have many unique common solutions, and that automatically implies that the two lines are actually consistent. So you can say a dependent pair of linear equations, or you can say a dependent consistent pair of equations. Okay, so that's basically that. That's basically the case where you have two coincident lines. For example, both of your equations can be represented by this single line over here. So now if we basically go back to the three situations that we had before, so this was actually the situation number 3, and I didn't really want to write anything here, but I did. So if you go back to the situations that we had before, so this was situation number 3, and this was situation number 1. So in situation number 1, you can see that we had this situation over here, and the two lines are intersecting at this point, and so the pair of linear equations is consistent, and of course not dependent. So here you have basically consistent and not dependent. Okay, so that is that. And then and then over here what we had was these two coincident lines, that is a dependent pair of linear equations. Infinitely many common solutions, so that's a dependent pair of linear equations, and of course dependent, and you can say that it is also consistent. But as I mentioned before, dependency basically implies consistency as well. So you don't have to I mean, if you don't want to, you don't have to say they're consistent. If you say that they're dependent, that automatically means that they're consistent. And then we have this situation over here where the two lines were parallel, and this is an inconsistent pair of linear equations. An inconsistent linear basically equation. Now, or a pair of an inconsistent pair of linear equations. Now, in each of these situations, if you basically go, if you take a look at the situation here, in each of these situations you have basically something like, for example, a1 times x plus b1 times y plus c1 is equal to 0, and then you have another equation as well, which is a2 times x plus b2 times y plus c2 is equal to x. And so you have all of these coefficients here, a1, a2, you have b1, b2, you have c1, c2, okay, and there is this relationship between the coefficients of your linear equations and the way that they are represented graphically, meaning that let's go back to, let me actually do a table over here, and then I'll tell you all about these equations. So basically, if you want to know that the relationship between those coefficients a1, a2, b1, b2, c1 and c2, and then the fact that they are basically consistent, inconsistent, dependent, intersecting, parallel, coincident, and the whole thing. And of course you will be able to use all of this information in order to analyze thousands of different cases. So you can use this information, and all we need to do, we just need to take a look at the different lines that we had, and then based on that we will be able to find some relationship between the coefficients and all of those different situations. So let's say that, let me draw a table over here. Okay, so let's say that here you have this, here basically we had situation number 1. Here we had this situation number 1, and the equations were x minus 2y. The equations were x minus 2y is equal to 0, and 3x plus 4y minus 20 is equal to 0. And then the next thing that we had was so these are the equations, and then we had a1 to basically a2, and then we had b1 to b2, we had b1 to b2, c1 to c2, and then we had the comparison of these ratios. And then we had the graph, the way that the graph showed itself. So it was a graph, and the algebraic way of representation. Okay, so if I do all of these, what we will have is basically something like this. So I have okay, so I have basically, I had this situation number 1 over here, and then I had situation number 2 where the equations were 2x plus 3y minus 9 is equal to 0, and then I had 4x plus 6y minus 18 was equal to 0, which were basically coincident lines. And then I had the situation number 3 where the two lines were parallel. So x plus 2y minus 4 is equal to 0, and 2x plus 4y minus 12 is equal to 0. And you see that a1 to a2 over here is basically a's are the coefficients of x's. So that's 1 to 3. That's 1 to 3. So b1 to b2 are the coefficients of y. So negative 2 to 4. And the c's are the coefficients, are the constants. So that's 0 to negative 20 over here. Over here you have a1 to a2 is 2 to 4, b1 to b2 is 3 to 6, and c1 to c2 is negative 9 to negative 18. And over here you have 1 to 2 for a1 to a2, b1 to b2 is 2 to 4, and c1 to c2 is negative 4 to negative 12. And the comparison is that you see that basically here things are not equal, meaning that the ratios are not equal. So you can say that a1 to a2 is not equal to, for example, b1 to b2. Over here you can see that this is 1 to 2, and this is also 1 to 2, and this is also 1 to 2. So that means that a1 to a2 is the same thing as b1 to b2 is the same thing as c1 to c2, and these were basically the coincident lines. Meaning that if you do the graph of these two lines, you will get exactly actually only one line representing both of these equations. And this is basically the situation where if you basically divide everything in this, for example, in this equation, divide everything by 2, you will actually get this equation up here, or if you in this equation multiply everything by 2, you will get this equation down here. Okay, so that's basically coincident, and here and over here the lines were intersecting. The lines were intersecting, and over here you can see that this is 1/2, this is again 1/2, but this is 1/3 basically. So you see that a1 to a2 is actually equal to b1 to b2, but is not equal to c1 to c2. And here was the situation where the two lines were actually parallel lines. Okay, so in the case of the algebraic analysis of these lines, you could say that when you have parallel lines you have no solutions. you have no solutions. In this case, you have infinitely many solutions, and here you have basically exactly one unique solution. Exactly one unique solution. Okay, and so again, from this table you can see that if you have two lines, for example, a1 times x plus b1 times y plus c1 is equal to 0, number 1, and you have another line a2 times x plus b2 times y plus c2 is equal to 0, number 2, that if these two lines are intersecting, then in that case a1 to a2 is not equal to b1 to b2. If these two lines are coincident, as you can see here, a1 to a2 is equal to b1 to b2 is equal to c1 to c2. In short, you can say that they are equivalent lines, and meaning that you can just simplify the line and then you will get the other one. And then in this case, if the two lines are parallel, then a1 to a2 is actually equal to b1 to b2, but is not equal to c1 to c2. And so you see that compared to this case, the line will be actually a little bit basically is going to have some sort of translation in which the line is going to be a little bit far off, and in that case we say that the lines are parallel, and that's basically what happens here. Okay, and so basically you can actually look at this as from a geometrical point of view, and also from the point of view of a theorem. I can tell you that if you basically state this in the form of a theorem, that for example, if two lines are intersecting, then a1 to a2 is not equal to b1 to b2, and the converse is also true, that meaning that if a1 to a2 is not equal to b1 to b2, then the two lines are intersecting. And then the other two cases as well, the converses are also true. I don't really know if or when we are going to prove these or not, but you can use them for now, and you can be sure that they have already been proved by other people, so you can already start using them, but when we actually get to proving them ourselves, I don't really know, not at this time. So that means that if you actually think of this in terms of if-then statements, that means that you can use this as the condition and this as the result, or you can think of this as the condition and then this one as the result, meaning that the converses are all true in the case of these three situations. And that's basically all that we have here for now. Now there is just one thing that we need to add to those three situations, and then we will do a couple of examples related to this table. Okay, so now let's go to basically each of those situations that we had before. I think they were from 14 to 17 to 16. So in this situation, you can see that the equations were basically these two equations. So you have y is equal to you have y is equal to 1/2 x, or you can write this as 1/2 x minus y is equal to 0. That's one of the equations that we have. And then also we have 3x. I'm writing from here, 3x plus 4y, and take this 20 to the other side, minus 20 is equal to 0. Okay, because I do need to write these in general form so that I can take basically the coefficients out. So once you do that, you see that a1 to a2 is equal to 1/2 to 30, 1/2 to 30, and b1 to b2 is equal to -1 to 4, and c1 to c2 here is equal to 0. There is a 0 over here, to -20. So this is 1/6, this is -1/4, and this is 0. So you see that a1 to a2 is not equal to b1 to b2, is not equal to c1 to c2, and you see that the lines are intersecting. Intersecting lines, and that means that you have exactly one solution, and that means that the pair of basically linear equations are consistent pair of linear equations, and and that's basically this whole situation over here. So let me actually take a look at these. Take a look at this situation over here. Let's see what I have. So you have a1 a1 to a2 is not equal to b1 to p2 to b2. The lines are intersecting, and you have exactly one situation, and that means that you have a consistent pair of linear equations. Okay. Now in the second situation that we had over here, the equations in standard form or in general form were basically 2x plus 3y minus 9 is equal to 0, and 4x plus 6y minus 18 is equal to 0. And so here basically a1 to a2 is equal to 2 to 4, b1 to b2 was equal to 3 to 6, and c1 to c2 is equal to -9 to -18. This is 1/2, this is 1/2, this is also 1/2. So you have a1 to a2 is equal to b1 to b2 is equal to c1 to c2, and that basically means that you have a pair of dependent linear equations, and what that means is that you have an infinitely many common solutions, and then that means that the lines actually coincide. That means that the lines actually coincide. And that's basically this whole situation over here. Okay, so that's basically this whole situation over here. About the next situation that we had basically the equations in general form, where x plus 2y minus 4 is equal to 0, and 2x plus 4y minus 12 is equal to 0. And here basically a1 to a2 was equal to 1 to 2, b1 to b2 was equal to 2 to 4, and c1 to c2 was equal to negative 4 to negative 12. So this is 1/2, this is 1/2, but this is 1/3. So you see that a1 to a2 is equal to b1 to b2, but it's not equal to c1 to c2. And you see that the two lines are parallel. You get a pair of parallel lines. So that means that you get an inconsistent pair of linear equations, and the lines are parallel, and you get no common solution because there is no point of intersection of the two lines. So that's basically this third situation over here. So now that we basically understand these three situations, we will go and solve a few examples over here. Let's see what we have over there. So example number, I think we have example number 4 somewhere over here. Okay, so for example, about, let's say that you have a pair of linear equations, and I'm going to do them over here. Let's say that you have a pair of linear equations, do them over here. A pair of linear equations, so it is x plus 3y. It is x plus 3y is equal to 6, and 2x minus 3y is equal to 12. Well, you can write them in general form, but you can also not do that, because you see that in this equation 6 has been taken to the other side of the equation. In this equation 12 has also been taken to the other side of the equation. So basically that means that they have changed signs together. That means that if you take, the ratio is going to be the same whether they are both on this side of the equation or on the other side of the equation. Meaning that right now the ratio of C1 to C2 would be equal to 6 to 12, which is equal to 1 to 2. Now if you take them to the other side of the equation, that would be x plus 3y minus 6 is equal to 0, and 2x minus 3y minus 12 would be equal to 0. And then in this case C1 to C2 would be equal to negative 6 by negative 12. Again, you'll get 1 to 2. So the ratios would not change, provided that both of them are on the same sides of the equation. Okay. So what that means is that, but it's always a good idea to write your equations in general form, meaning that you can always write them in this form to get rid of any kind of confusion that you might have. Okay. So what happens is that in this case, let me first, in this case, what we want to do here, we will check graphically and also using the coefficients whether this set of this pair of linear equations has a solution, doesn't have a solution, is consistent, is inconsistent, is dependent, and so on and so forth. So if you want to draw this line, so the first one, for example, this line over here, x plus 3y is equal to 6. Well, it's always a I mean, normally what you would do in order to draw a line is that you basically have to try a few values. For example, if you try x is equal to 1 in this equation, then this equation becomes 1 plus 3y. 1 plus 3y is equal to 6, and then 3y is equal to 6 minus 1, and then 3y is equal to 5, so y is equal to 5/3. Okay, so you see that if I set x is equal to 1, for example, I'll get y is equal to 5/3. So 1 comma 5/3 would be 1 point on the graph of this equation. But now it's kind of not easy to plot such points, especially if you were doing it on graph paper or on square paper or something like that. It would not be easy to find 5/3 on your graph paper, meaning that you would it's not very straightforward. So what you can do in order to get rid of such problems, what you can do is that you can basically input the kind of values where you would get round numbers or whole numbers or integers, meaning that the number that you get over here as y is not a whole number, it's not an integer, it's a rational number. And it's not easy to plot rational numbers on graph paper. On the other hand, if you have the same equation and tried, for example, x is equal to 0, then you would get the same equation would be 0 plus 3y is equal to 6, and then y is equal to 6/3, y is equal to 6/3, which is equal to 2. Okay, so that means that basically the point 0 comma 2 is on your is a point on the graph of your on the graph of the line, and now it's easy to find 0 and 2 on your graph paper, meaning that you could simply say that, okay, so if this is 0 and 0 comma 2, this point would be the point over here. On the other hand, this point would be 5/3 would be 1 and 2/3, so that would be 1 comma 1 and 2/3, and then this would be, for example, I don't know, 1 and 2/3 would be some point over here, right? So now, of course, this way I can draw the graph, but it's not very accurate. But and so basically, what you usually do to draw these graphs, and I'm sure that by now if you're watching these videos, you know enough about these about drawing a graph of an equation or a function, that I don't really have to talk about these things over here. So, but just for the sake of this discussion, what you would normally do is that you would try, for example, some x and y's. For example, x is equal to 0, y is equal to 2, or x is equal to, or you set, for example, I don't know, x is equal to, where is my equation? Or x is equal to, for example, 3, for example, and then y is equal to 1. Because if x is equal to 3, then 3 plus 3y is equal to 6. So 3y is equal to 3, and then y is equal to 1. Okay, so then you would get these 2 points, and then 0, 2 would be this point over here, 3, 1 would be this point over here, and then you would probably do the graph like this. Okay, but this is, I mean, trying these values is of course a good way to draw the graph of these functions. On the other hand, what you can do is use the y-intercept and the slope of these lines, and then that way you can also draw the graph of these lines, meaning that you can basically take this equation over here, 3y plus x is equal to 6, this first one over here, and then you want to separate your y, so 3y is equal to negative x plus 6, and then y is equal to negative 1/3 x plus 6 divided by 3 is equal to 2. And now this is this number over here is the slope of your function, of the graph or of the line, and this is the y-intercept. Okay, so again, this y-intercept is the point where the line goes through the y-axis, and if a line is supposed to go through the y-axis, at the y-axis, basically your x-intercept is basically always 0, because at the y-axis itself the x is always equal to 0, and then you can move along this line over here. So the coordinates of this point would be 0, 2, which would be some point over here, for example, 0, 2. Okay, and the slope of your graph, or I'm sorry, the line is negative 1/3. So we said that, I'm sure you already know this, I have already talked about this. So the slope is the rise over run, meaning for a unit horizontal change, how much vertical change you have in the line. So basically what we have here is that for 3 units of horizontal change, we have -1 units of vertical change. So that means that this is my run, 3 horizontal units. So if I take this point as my reference point, I have to run for 3 units, and I'm going to end up over here. And then I have to rise -1 units. So rise -1 units, meaning that I have to fall by 1 unit. So I will end up over here, and that's going to be the line that I'm looking for. That is the line that I'm looking for. Okay. Now the other line that I want to draw is, so this is x plus 3y is equal to 6. The other line that I want to draw is this line over here, which is 2x minus 3y is equal to 12. Okay. And so again, you want to separate your y, so -3y is equal to -2x negative 3y is equal to negative 2x plus 12, and multiply everything by your negative 1, you'll get 3y is equal to 2x minus 12, and then divide everything by a 3 to get rid of this 3 over here. So y is equal to 2/3 x minus 12 divided by 3 is equal to 4. So again, this is your y-intercept, which is 0, negative 4, and this is your slope. So the line becomes 0, negative 4, which is basically 1, 2, 3, and 4, and so that is 1 point on the graph of the function or the line, and 2/3 would be the slope, meaning 3 units of run. If I take this point as a reference, 3 units of run gets me to here. Okay, 1, 2, 3 units, and then 2 units of rise. So 1 and 2, that gets me to this point over here. And then if I connect these points, these 2 points together, I'm going to basically the graphs are going to intersect at this point. Now whatever that point is, I don't really know, because 1, 2, probably 1, 2, 3, 4, 5, 6, 6, 0. Probably 6, 0. We will see about that. Okay. So, but now the important thing over here is that you need to basically, you always use some sort of calculator or some sort of graph or electronic device in order to have the graphs drawn for you. But you can also do some calculation in your head as well, in order to find out what sort of lines or what sort of system you're dealing with. Meaning that once you have written your equations like this in general form, you see that over here a1 to a2 is equal to 1 to 2. Your b1 to b2 is equal to 3 to negative 3, which is equal to negative 1. And c1 to c2 is equal to negative 6 to negative 12, which is equal to 1/2. Now, basically the first two things that you need to compare is a1 to a2 and b1 to b2, and you can see that a1 to a2 is not equal to b1 to b2. That means that the two lines are intersecting lines. And since you have intersecting lines, what that means is that you have exactly one unique solution. Okay, which is essentially this point over here where the two functions basically intersect. Exactly one unique solution, and the system is, or you have a consistent pair of linear equations. Okay, so that's that. Now, just for the sake of this one, I'm just going to draw the graph for you as well, in order to see basically where this point is on the x-axis. So I'm going to write this as x plus 3y is equal to 6, and here I'm going x plus 3y is equal to 6, and 2x minus 3y is equal to 12. And you see that the point is 6, 0, as we kind of predicted over here. 6, 0 over here. And these are basically the two lines intersecting at this point over here, which is 6, 0. Okay. So that's basically one example. Let me see if we can, if I find a good example over here as well. We will do a couple more as well, and we will get to the rest of the things. Okay, so there is another question here that is kind of interesting algebraically, and then we can do a couple of things with that. So let's say that I know that, for example, Susan bought basically a number of pants and skirts. Okay, and I know that the number of skirts, skirts is 2 less than twice the number of pants purchased. Is 2 less than twice the number of skirts. No, I'm sorry, the number of pants. And also the number of skirts is 4 less than 4 times the number of pants. Is 4 times the number of pants. Is 4 less than 4 times the number of pants. Is 4 less than 4 times the number of pants. The number of pants. Okay, so now if you want to figure out the number of pants and skirts that Susan bought, what you can do is that you can denote the number of pants by x, for example. The number of pants by x, and the number of skirts you can denote by y, for example. You can essentially take any other two variables, for example a, b, b, c, c, d, or whatever you want to choose, but this way basically you can it fits with everything else, because, for example, when you have a two-dimensional plane like this, then you basically, by convention, we say that this is the y-axis, this is the x-axis, and so on and so forth, and so then everything this way fits together. Otherwise, you can do anything that you want, as long as you're consistent with what you do throughout the problem-solving process. Now, if I denote the number of pants by x and denote the number of skirts by y, I know that the number of skirts, which was basically y, is 2 less than twice the number of pants. So 2 less than twice the number of pants is twice the number of pants would be 2x, and 2 less than that would be 2x minus 2. So y is equal to 2x minus 2. And also I know that the number of skirts, which is again y, is equal to 4 less than 4 times the number of pants. 4 less than 4 times the number of pants. 4 times the number of pants would be 4x minus 4, 4 less than that. So now I have a pair of linear equations in two variables, and well, if you look here, what you have is this is equal to basically 2x minus y minus 2 is equal to 0, and what you have here is 4x minus y minus 4 is equal to 0. And then a1 to b1 a1 to a2 for example, a1 to a2 is equal to 2 to 4, and b1 to b2 is equal to -1 to -1, and c1 to c2 is equal to -2 to -4. So this is 1 to 2, this is 1 to 2, this is 1, and this is 1 to 2. So you see that a1 to a2 is not equal to b1 to b2. So therefore you can expect to have one unique solution. You can expect to have one unique solution, meaning that you have two intersecting lines, and it's a consistent pair of linear equations, and that's basically the whole story. Okay, so now in order to do this also geometrically, to solve the problem geometrically, what you can do is that let me write down this thing down here. So basically what you can do is that you know that over here you have y is equal to 2x minus 2, so that means that your y-intercept is -2. That's one point, and the slope of the line is 2. So that means that for 2 is the same thing as 2 to 1, and that's the slope of the line. That means that for one horizontal change, you have 2 units of vertical change. So if you go basically one horizontal change, 2 units of vertical change, that means that 1 and 1, 2. So you'll end up over here, and you will have a straight line like this. So that's going to be y is equal to 2x minus 2. In the case of the other line over here, you have 4x minus 4. So the y-intercept is -4, so that would be this point over here, and your slope is positive 4. That means that 4 to 1, which is for 1 unit of horizontal change, you have 4 units of vertical change, which means 1 unit of horizontal change would get me here, and then 4 units I will be essentially over here, and that means that the two lines intersect one another at this point, which is 1, 0. That means that your x is equal to 1 and your y is equal to 0, meaning that your x is equal to 1 and your y is equal to 0. She actually bought one pair of pants and no skirts. Okay, one pair of pants and no skirts. And then and there is one more way to actually solve this problem, which we will get to shortly in the next videos. But I want to show you how you can do that as well, so that you can take care of your problems easily. So So what you can do here, you see that basically the equations that you have are y is equal to 2x minus 2 and y is equal to 4x minus 4. So I can somehow basically find for example y or x in terms of the other, and then put it in the other equation, so that I can solve one of the equations, and then I can basically go back and do the same thing, and so that way I will be able to solve the problem without actually having to draw a graph or something like that. So basically my equations are y is equal to 2x minus 2 and y is equal to 4x minus 4. Okay, so what I can do, I call this number 1 and call this number 2. So I take equation number 1 and write it as, for example, you don't even need to do anything here. So you know that y is equal to 2x minus 2. So y in terms of x is basically, y in terms of x is y is equal to 2x minus 2. Okay? And so I can take 2, equation number 2, and instead of y, I can write y in terms of x, which is 2x minus 2. So your equation is y is equal to 4x minus 4. So instead of y, I can write 2x minus 2, which is equal to 4x minus 4. So then you can solve this equation in one variable. So in 2x minus 4x is equal to minus 4 plus 2. And negative 2x is equal to negative 2, so x is equal to positive 1, right? Which is in agreement with what we got here. So x is equal to positive 1. And then what you can do is that now that you know that your x is positive 1, you can put it in any of these two equations and get the other variable, meaning that, for example, you have 2 basically was y is equal to 4x minus 4, and so if x is equal to 1, then y is equal to 4 times 1 minus 4, so y is equal to 4 minus 4, which is equal to 0. So then you know that x is equal to 1 and y is equal to 0. That's your solution. We will have a couple of such ways to solve these problems. And that's basically the whole story here. Now, in the next videos, we will take a look at a couple more things related to these to this whole story. I will go through some examples. We will have some more material here to cover, and it's going to be all fun. So I'll see you in the next video. Thank you.